Hi everyone. First of all, thank you for being here. My name is Hindol Rakshit. For those of you who do not know, I also am a student of ISERC. I studied in ISERC in 2009. I belong to the first batch of ISERC. Graduated in 2014, and then later on, I went on to do another master's in Europe. And currently, I'm working in a startup in Germany as a data scientist. And I know that it's a Sunday, so of course, like a lot of you might not be really interested in getting into deep science or research related topics. So I promise whatever I have prepared today is a very basic presentation that most of you will understand very easily. And it's actually more than a presentation, it's just a fun little exercise to get you interested in machine learning. And of course, machine learning, some of you might have heard about it, some of you might not have heard about it. It's a very interesting field in computer science, which I work on. And let's begin talking about it. So, okay, no, first of all, like if you see the topic of the presentation is like the title of the presentation is what drives a search engine? And the simple answer is machine learning drives the search engine. But of course, like just knowing this is not enough because I see a lot of times in the industry, a lot of people come with some knowledge in machine learning, but they do not really know what are the use cases of machine learning in the industry. So what I will do here today is take you through some simple use cases, which will help you prepare to understand like why should we actually learn machine learning and how can we actually use it in the industry. So in the industry, data science related problems can mostly be divided into two groups. All right. One group of questions are related to search. Another group of questions are related to forecasting. Now, search is something that a lot of us are familiar with. Let's say if you have a question and you go to Google and you make a search, that's a search problem, but that's not it. That's just like one tiny section of what search problems are. Let's say you join a game and the game is trying to find a Facebook friend of yours who you can play with in tandem. That's a search problem. Similarly, let's say you joined Facebook and Facebook was trying to recommend you one person that you may or may not know to add as a friend. That's also a search problem. And today I'm not going to talk about forecasting problems. So forecasting is another interesting thing where, for example, like this is the statistics of a player. And given that, what do you think this, how do you think this player will perform in the next game? That is a forecasting problem. So let's say a company is trying to decide, given its profit in the last quarters of business, how will the profit look like in the next quarter? That's a forecasting problem. So these are the the main two divisions of problems that data scientists deal with uh, in the industry. And today, I'm just going to talk about search because that's what I mainly work on. And to start with, let's actually begin with the basic structure of a search engine. All right. So a search engine is not just a database. Is what happens is that there is a query. It goes into a database, and we have a selected outcome. So we give in the query. It goes through the database, and we expect an outcome. And now this is very important to know that when we talk about a database, it's not just data. And I'm saying this because that's the usual misconception. When we talk about a database, it's actually data plus some sort of a structure. And I want you to keep in mind this thing because we will revisit this slide multiple times, revisit this concept of data plus structure multiple times in this presentation. By the way, everyone is silent. So is it audible to everyone? Just want to make sure.
Yes, yes.
Okay, perfect. So of course, there are many technical layers to this search engine, but not going into those technical layers, what we will try to do is we will try to build a very simplistic search engine today. All right. And in this search engine, what we have is we have a query. It's the picture of an orange, and we have an outcome. The outcome is the statement says this is an orange. Then the question is, what should be there in the database, right? And so the most naive answer would be the database should contain a single item and the item, the name should be orange, and the image should be associated with this, so that this image actually relates to the query that comes from here, and the name is actually related to the outcome that comes from here. And this we can call an evidence-based approach, where we are looking at what kind of queries that people are presenting, and based on that we are just populating the database with items which are like commonly searched. But the problem is, for this problem, this will be okay. But let's say we have this kind of a question where this is the query now, and this is the item now, then obviously the search engine will fail, because we have trained the database to understand this picture. And now what we are presenting, based on our human intelligence, we know that this is also a picture of an orange, but this image does not match with this orange. And that's why this will fail. So what we can do here, we can actually take two approaches. First of all, we can actually stay with the evidence-based approach, and we say that, okay, we're talking about oranges, so let's actually fill up the database with all kinds of images of oranges that we can find. So that's one approach. Another approach would be a functional approach, where we say that, like, what does an orange actually look like? And then we can actually get some geometrical variables. For example, the name is orange, the shape is circular, the color is a particular RGB value. And here, what we can see, that we can avoid the specific differences between different images and define a general structure by which we will classify something is an orange or not an orange. Right. Now, of course, we can understand that both of these approaches have some benefits as well as some disadvantages. Firstly, if we look at the evidence-based approach, if we have a database where we have a lot of pictures or a lot of evidences, then what happens is that it increases the statistical chance of getting a match by creating an exhaustive database. But at the same time, if there is even a pixel level difference between the query and what is there in the database, then it will throw out the error, throw out the query and throw an error. On the other hand, if I see the functional approach, one huge benefit is that it's cost effective, because like when you keep something in a database, it takes a little bit of memory, and that you're charged for it, right? But if you go for a functional approach, then you actually what happens is that, like, you do not need to store a lot of information in the database. You're getting it through a functional approach, and then it's like much cheaper to concentrate. But can anyone tell me what would be the con, what would be the disadvantage of this functional approach? It's an open question. Can anyone tell me this?
The disadvantage would be if the orange is, let's say, not that round or of some other shape, or it is crooked or something, then it might not recognize.
Correct. And there is another disadvantage, which would be like it will classify anything that is orange color and round as an orange, right? It will not try to actually go into the further details of it. It will just see that, okay, this is orange, this is it's a particular color, it's a particular shape. Okay, let's classify it as an orange. So that means it increases the chances of false positive. And that's why what we need in realistic systems is actually a combination of the evidence-based approach as well as a functional approach. And now, if we remember what we showed in the first slide, that a database connected to a search engine is not just data, it's data plus some structure. So when we say structure, it's actually a combination of evidence plus some functional approach. So let's actually try to do that in this system. So let's say we start with an evidence-based approach where we have a database. We say that it's an item called orange, and instead of image having a single image, like I have collected, let's say 9 different images of oranges that I randomly found in Google, and I populated the database. Now, right now we're actually getting completely into like a job interview like zone, where I want to ask you, just looking at this data, just looking at these images of oranges, how would you try to impose some structure on these database? I'm not going to give you any more information. I'm just going to say that just look at these images, look at these 9 images, and try to tell me This is also a question to you. Try to tell me how would you impose some structure on this database?
We will try to see like how many pixels are covered and what is the size and what structure do the boundary pixels form after which white color starts and what kind of ellipses they are and the
So
color variation.
I'm happy that you're already talking about the white color because that will become very important right now. But even before that, like let's say when you look at a group of students in a class, what is the most basic structure that you can think of?
That
Even
they
before
look similar.
pixels, even before like the shape, what is the most basic observable structure that you can look at?
Circular, spherical.
No, here I'm assuming that all of the entries are circular.
Hmm.
Orange in color?
No, which
Let's
class
assume
they
that there is
class
going to
they
be
belong
oranges,
to?
which class they belong to. For example, as I said, like when we look into a group of like students, I think a basic classification, a basic structure would be how many males are there and how many females are there, right? Because that might be the most observable attribute among that group. And here, I don't know if it's like, tell me if it is not visible properly, but I think it should be visible that there are oranges which are peeled and oranges which are not peeled.
Oh, okay, okay. Got it. Peeled oranges and non
Yeah,
and cut oranges as well.
Yeah, cut
Whole
oranges
oranges.
as well, peeled oranges as well. And let's say for now, like the most basic structure, we say that oranges with the skin and oranges without the skin, right?
Hmm.
So that would be one structure where we take this database and we put it through a classifier and we group it into two different classes. Where in one class we have oranges with the skin, and on another class we have oranges without the skin. Now, again, going back to the database, I will say like just looking at these pictures of oranges, how would you design this classifier? And that is perhaps the most important question in this presentation. I'm not gonna tell you like what would be like a pixel level information, what would be like just looking at the images, what would be like a very basic understanding of what can be a orange with skin in this database and what can be an image of a orange without the skin.
The green part. The
The
green part
green
of the orange.
the green part of the orange is actually one good thing. And similarly, if you think of the same way for the skinned oranges, what would be that?
The central white part
The
and
central
the
white part. Exactly. So that's actually like a very nice thing. Either the green part or the central white part, right? Because if we look at the images, what we see that forget about whatever you know of oranges, because when we say we have defined a database, we mean that we are not going to consider any other images from elsewhere. We are just going to consider about all the information which is situated within this database. And based on that, what we can see that all of these are kind of orange, but it's not entirely orange because we see two colors. The dominant color is orange and the other color, which is not so dominant, is white, right? And white is actually there in almost all the images, but in the peeled or in the cut oranges, what we see is that the center is actually white. Is that understood? Is that like clear?
yeah.
So that actually can be a criteria by which we can classify. So let's actually try to like break it down into an algorithmic format. So let's say if we take the query as an object is the variable. So first of all, we take the shape of the object and say if it is circular or not. If it is not circular, then we quit. We don't care if it's not circular. Now, if it's circular, then we check the color distribution. And in the color distribution, what we do is like we take the color and the percentage coverage. So let's say hypothetically, we can have a situation where 98% of the color is orange and 2% of the color is white. So if you check the argmax, the color with the maximum like distribution, maximum coverage is orange, then we define the name as orange. But then we further go forward and we say that if the color of the center is white, so this is, by the way, the RGB code for the color white, then we can define it as peeled or unpeeled. All right. Does that make sense? Or should we like go back and like explain this again? Because this is very crucial. Does that make sense? Does anyone have any problems so far understanding?
What if we took the image of the cut orange from horizontal level, where the white cannot be seen?
Exactly. So that comes into, uh, so you're saying that from which image are you saying? This image?
No, no, the bottom image, the sliced one. Let's say we
Yeah.
took the image from an angle from which the white cannot be seen, basically from the ground.
Then you cannot classify it as a peeled orange. You will classify it
No,
as an
what
orange
will
with skin.
what will be in case of this the peeled orange? Only the peeled orange, which is not cut it.
Yeah, we will actually, I would say just wait for 2 minutes and we will actually get to this image, because this is like it's there specifically to demonstrate this thing. All right.
Hello.
Hello. Yes.
Yeah. So in case of unfilled oranges, if we put the picture, if we
I'm sorry, you're not very clear.
Abhinav bhaiya, your voice is breaking.
I will write in chat. Okay.
Okay, so let's actually wait with the question and let's like move forward for now a bit. So what I really want to say is that this might have seemed like a very primal exercise. And here, what I have presented is one algorithm. There can be multiple algorithms that you can design to define like what should be a perfect classifier. But this essentially is the job of a machine learning engineer. Most of the time, you're given databases and you're assigned to classify data into different classes. And that's what you have to do as a data scientist in the industry. So if there's one thing that I would say that you take from this presentation is that a search engine is as good as the labels associated with the database. Because whenever you classify something, originally what information we just had the information that this is an image of an orange. But then you keep classifying, and by classification you keep adding new labels to the data, to new labels to each of the data points. And the more labels you have in your database, the better, the more observable and more searchable is your database. And that's how like you make a search engine more robust. Now of course you have made a classifier, but of course we don't know how good is the classifier. We have an expectation that this will do the job properly, but will it or not, that's we have to see. Because let's say this is our expectation. I think someone asked like, why is this thing in class 2, right? But based on the classifier that we have designed, what will happen is that this will be the reality, right? Because we have only checked whether the center is white, and based on that criterion, this cut oranges will fall into one class, and all of these oranges with this peeled orange will fall into class 1. So I have two questions. One is like, what
So one,
is that yes.
no. I did not tell
No.
anything. Just he wrote the question.
Yeah, so the thing is like, what can we do to make sure that this orange falls into this class? Another thing is like, is there something wrong with the way we have defined our classes? Let me know. Hello?
Yeah, Abhinav bhaiya is wrote that we have to do some image correction before letting it to be matched with the database.
Yes, that is true. But what does that really mean? What kind of image correction?
Actually, he wrote it in a previous comment that what if the picture having the light blend in the center of unpeeled orange Will
Mhm.
all that also be classified as peeled?
The light, which one? This one?
No, let's say like Abhinav Bhaiya's question is that let's say while photographing the orange, the
Mhm.
light, the glare which is coming off it is focused at the center of the orange. So
Yes,
that
then it
part
will be classified based on the classifier that we have designed right now. It will be classified as a peeled orange. Does that make sense? It's a false positive.
so like one thing I guess you can add to our classifier for this thing is that the color will be not as bright as the outer skin of the orange
Yeah,
and not as perfectly orange.
not as perfectly orange, and not just that, the white, the distribution of the white, you can actually make a threshold, right? Because if you see this images, the white is there, it's basically the indirect reflection of the white light spotted on this orange, so it's very minimal. On the other hand, here you can say that like the white is much more like relevant in this picture. You have more coverage of white in this picture than this image.
Yes.
Another thing that you can say that our original like definition of the class system is wrong. Here I have actually tried to class it into two groups forcibly, whereas there should be actually three groups, where the complete like round oranges, the unpeeled oranges is one class, the sliced oranges is one class, and this is another class.
Yeah, this thing is written by Ritam sir that we can make classifier as peeled, unpeeled, and cut oranges.
Yes, not just that. I'm here to tell you that in machine learning, there is no absolute right answer. Whatever you're saying is an assumption. It's the best case assumption that you can take here. All right. So even then, so what will happen that you can initially class it into two groups, where oranges with skin and oranges without skin. And then you can say that within the oranges which are without skin, you can further classify into oranges which are sliced, oranges which are not sliced. And of course, you can like keep going again and again and again, and that's how you will actually design a classifier. But this, since like it's a very basic assumption, this is what I took. Like I see the oranges and I see that, okay, let's take a very statistical approximation, a very simple statistical approximation, and try to divide it into two groups and see what happens. Now the most important question for you people is that, can anyone tell me what is the efficiency of this classifier? And efficiency relates to what was our original assumption, what we designed, and what we got as an output. Our original assumption was that the oranges should be divided into two classes. One class is with the skin and another class is without the skin. And then this is what we got as the outcome. Then what should be the efficiency of this classifier?
Is it somewhere near 80% efficient?
Good question. Any other guesses? I can see why you're saying it's 80%, but it's a bit further than that.
It's
It's a bit more than that. Because you are
75% written by Jyoti Ranjan.
no, it's not 75%. So 85%, whoever said 85%, I'm guessing that you meant that originally you were supposed to classify five oranges in the second class, but you got four of them right. That's why you said 80%.
Exactly.
But but you're only thinking of one class. On the
But it
other
should,
class,
it's like 8 by 9 times 100, right?
exactly.
Yes.
Yeah, on the other clans, you were supposed to get four ones, and you actually got those four ones right. So this classifier might be completely wrong, like or partially wrong for the cut or peeled oranges. But when it's a round orange, then it's actually perfectly fine. It's actually a 100% efficient classifier in that sense. So on average, we can actually say this is a 90% efficient classifier. Does that make sense?
Yes.
Okay. Now,
but we are
yeah,
uh,
go ahead.
so we are computing the efficiency with respect to the data set that is already provided.
Exactly. That's all we
Okay.
can do. When we are computing the efficiency, we have no access to other data. We have no access to other data that might be available. We can only check based on the training set, the data set that is provided to us.
But on the other hand, how about a case where we have a training set and we have a set on which we are doing the experiments
Exactly. So
and then find the efficiency?
yeah, but based on that, you have to create the training set, right? What we are doing here, I'm actually glad that you said it, the word training set. This is actually, we are creating the training set here. So that once you have this training set, we get an entry from outside and that can be classified. And that's the testing set.
But shouldn't the efficiency be dependent on a certain testing set? So once we train it, and then we can use a testing set on which based on which we can find the efficiency.
I'm talking about like one step before when we don't, let's say you just have a data set and you have no idea what should be the input and you have to create the training set for yourself.
Okay, okay.
I see what you're saying that you actually to properly like create the efficiency, properly understand the efficiency, you need an external like a training set. But I'm saying that even before that, that is only valid when you have some like actual confidence on the training set, right? When you do not have
Uh,
training on a confidence on the training set, then actually even if like your efficiency based on your testing set says like 100%, then that's actually not true.
exactly my point. I mean, we can always design the classifier in such a way so that the
Mhm.
efficiency is 100%.
100%. Yes, yes, of course. But the thing is like how you have to put the effort to design the how do you want to put the effort to design the classifier? That's the question. It's actually we are getting into a zone of effort versus efficiency. How much effort do you put to get how much efficiency?
All right.
All right. So
Yeah, I think I get your point. I think I get your point.
yeah. So basically, what I'm trying to say is that while classifying the original data set, what we saw is that with just one statistical observation, you can get to almost a good classification. Of course, there are false positives. This is a false positive here. But in order to further improve the classifier, you have to put in more statistical efforts that might not be enough. And first of all, that might not be balanced given that what is the reward? The reward is like another 5 or 6% jump in your efficiency. And this is actually a very important thing. And I'm sorry for the like bad graphics here. This is I just like prepared it by hand, is that if you look at the efficiency, how efficiency increases, and given that the effort that you put into creating a classifier, you will see that there is a time until which the efficiency increases almost proportionally with the effort that you put. And then comes a point where, in order to increase the efficiency even a little bit, the amount of effort that you have to put becomes like significant. And then what happens is that computationally is not really like optimized, it's not really optimal to put that much effort. So in reality, when in industry, the all the soft search problems, all the search engines that you see, none of them are 100% correct. What we do is we balance between how much effort that we need to put versus how much outcome we are going to get, how much efficiency we are going to get. If we see that we reach a point where with a significant amount of effort we are getting quite a significant amount of efficiency, then we are happy with it. And that's actually the exercise that I want you to do even before like looking into machine learning or any other kind of like actual courses, that you need to take some data and try to build like a really simple search engine model from it. And then first of all you design the classifier, you try to classify the data into different groups. How do you do it? What should be your approach? And ultimately, what is the efficiency of your approach? And what is the most importantly, what is the optimal efficiency of your classifier? How to make a classifier that is optimally efficient given the database that you have. All right. Now, to help you with that, what I'm going to discuss is some very simple two problems. It's basically, these are not related to computer science. These are very basic analog problems. And what we will try to do is we will try to interpret these two as machine learning problems. So let's take the first example. It's just a general statement that an interviewer comes to the campus with an offer of a machine learning job and selects the best candidate for the job. Now, what we need to do is we need to interpret this statement as a machine learning problem, as a database, as a classified database problem. Now, can anyone tell me how can we approach to do it?
Maybe people who know about machine learning and don't know, that can be the first basis of the classification.
Exactly, because if you always go back to the first slide, which is like, what is a search engine? Then you need to answer this question. Then what is the query here? What is the outcome here? Because if you have these two things, then it becomes clear. Then what is the database? And once the database is clear, you need to put emphasis on how should be classified. So here the query is simple. The query is like an interviewer needs someone who has machine learning experience, and the outcome is a candidate who is the best person for the job. So the database is actually the pool of students from which the interviewer can choose. Then of course the interviewer, the most like brutal way, brute force way would be for the interviewer to go from one person to another and ask and like check their skills, right? But a classified way would be the interviewer actually checks for how many of the students actually took a particular computer science course or not. And then the interviewer knows that, okay, this group of students actually didn't take this course, so they're not really relevant for this job. Only these group of students are relevant. And the interviewer can, of course, like further say that, okay, among these group of students, these students got a significantly good number of marks in the subject. So maybe this is my interview pool. Now, here's actually, again, there's another interesting thing about how the efficiency becomes very, the effort becomes very steep with the efficiency. So far, with a very simple classifications tools, we have gotten to a hugely efficient small pool of students who can be eligible for this job. But now, if the interviewer actually wants to further classify this group of students, you need to actually look for further statistical efforts and further like questions and like criteria to further divide this group in until you finally get the group that you're satisfied with. And here's, it's actually a good example of how like you actually put the effort until an optimal situation in the search engine. Another example, and this is actually a really interesting example. So, given the time constant, a student decides to study the three most important chapters for the examination. So, can anyone tell me that what is the query, what is the outcome, and what is the database here?
The query is, I guess, the three chapters which I need to find which have the highest probability of coming in the exam.
Yeah.
So the outcome should be that out of those three, at least two come for the exam. And to classify that, I guess I need to see what came before and
No,
like
tell,
how
tell me one thing, like what is the database here?
the database should be previous year's question papers, I guess.
No, why not the syllabus itself?
Like, mm, I mean, then we have to assume that some chapters are lengthier or more focused upon than other.
Exactly. So what happens is that I actually asked this question to someone in an interview, and straight away he said that the database here is actually the syllabus. And that's why I put it here, because this is an interesting case where the database is not the syllabus here. In fact, the query is the question paper here, and the database actually is different instances of the syllabus with a particular group marked out, because let's say these are the most important zones from which the question came, and based on that the student actually checks, let's say, a particular statistically significant area as the best chapters. All right. Now, I promise that I'm not going to get into very technical in this. I just wanted to keep it very like simple and playful, just to get you interested. But what we have been discussing so far are examples, are very naive examples of a particular field of machine learning called supervised classification or supervised learning. And in supervised learning, what happens is that you have a training set. The training set is actually a well classified database. So it's not just a collection of data points, but it has data points with each data point is associated with multiple labels. So that when you get a set of queries, which is actually your testing set, you apply the classifier that you create. And based on that, your goal is to properly classify the testing set. And similarly, just like we have supervised classification, we also have unsupervised classification, where you do not have a training set, where you just look at the testing set, and you look at the properties of the data in testing set, and based on that, you like apply some logic to understand what should be different clusters of queries here. Now, if you really want to get into some real applications, first of all, the image, the orange like example that we did, it's actually a classic problem of facial recognition. What happens in face recognition is that you actually, at a crude level, when you're creating the training set, you're actually measuring the distance from, let's say, the nose, tip of your nose to your mouth, the length of your eyes, etc. And you're creating training sets based on which, when you look at a query, which is actually an image, you can say whether this person is familiar to you or not based on the database and based on the labels on the database. Similarly, spam detection, how Google actually, like out of all the mails you get, some of the emails actually get your spam folder versus some of the emails stay in your normal folder, is based on some, a lot of times it's actually keywords. So when you have some particular keywords in this email, then Google can understand that, okay, this is actually a spam email. And over the time, when you keep classifying this as spam and non-spam, you create a training set. Based on that, when you see an email, you right away know whether it's a spam or not. Now, interestingly, this is one of the latest applications that this has been doing is in human resources of big companies. CVs are actually classified using the spam model. So what happens is that an HR rep gets 500 or 600 CVs from different students, and they don't have time to actually look through all the CVs. So what they do is they run it through a spam ham model, and they identify keywords. If those keywords are there in your CV, they keep it, and if those are not available, then they throw it away. And then it comes into a small group of CVs that they are actually manually checking and then like calling for interviews. Similarly, recommendation engines, like whenever you watch a movie, let's say Netflix, and then Netflix says that, okay, you have watched this, now I can recommend you this another movie. And that's completely based on this labeling, because all of these movies have particular labels associated with them, which has been developed so that they know which clusters, which classes these movies or serials belong to, so that you watch one thing and then another thing is recommended. So these are actually some like applications, especially the spam detection model is something that I particularly work with. But of course, the other ones are also based on this simple principle of supervised learning. Now, if you want to do some like further readings in this, I would suggest Hasty Tipshirani Friedman, which is a basic, like a standard textbook on statistical learning. Another thing is in YouTube, what you can find is there is a lecture series by Ulrike von Luxburg. And this is, I'm actually a bit biased to this because like I studied under Ulrike von Luxburg in University of Hamburg. So it's the same curriculum that I went through that it's also available right now for free in YouTube that you can watch and learn. Another thing is like in machine learning, it is not a theoretical subject. This is extremely application heavy. So you not just need to design algorithms, you also need to implement it. And the easiest way to do it, I would say, is to go to some free course. For example, Udacity offers a course called Introduction to Machine Learning, where you not just get to learn the basic concepts, but you also get to like write Python codes or R codes to apply, and you get data sets on upon which you can apply it. So that's it, actually. Yeah. Now, if you have any questions, you can let me know. Hello.
Yeah, you are
Yeah.
audible.
And Bhaiya, I have a question regarding the classifiers.
Yeah.
So, do we need like human interface to classify or to put labels to each kind of object we classify, or we use some machine learning or some learning algorithms to
Very
handle it?
quickly, can you tell me what would be the benefit and what will be the disadvantage of using like a human classifier?
Firstly,
Like,
that would be like, yeah, you if you are using humans, then it would be like too hectic, or it would be cumbersome for a person to add labels to everything we classify. And
but
also,
that
it
would
would
be the
not
most
be,
that would be the most accurate classification, right?
yeah, but at the same time, that would be like quite slow to add labels to
That would be quite slow
every
to add.
object.
It will be extremely cumbersome. A human mind cannot really process like millions of data points. But even if a person can classify 10 different data points, then you will see that these are the most correct data points. It's any day it will be more accurate than any algorithm, any classifier than you can design. But the problem is the statistical goal here. We instead
Mhm.
properly classifying, like accurately classifying 10 data points, we want to semi accurately classify at least a million data points. And that's where machine learning
Yeah.
comes in. Actually, that's why you need machine learning, and like you cannot just rely on humans in this thing.
Okay.
Can
Yeah.
I ask one
Okay.
question which
Thank
is
you.
not exactly
Of course.
hello? Can I ask one question which is not exactly like completely related to this? I mean, a little bit outside of it.
Yeah, yeah. Any
So
question
like,
is okay.
okay. So like, I wanted to know what is the main principal difference between machine learning and deep learning?
Deep learning is a part of machine learning.
Okay.
So machine learning, as I said, like there are two main parts, right? There is supervised learning, there is unsupervised learning. And when you go to study supervised learning, there are multiple different approaches. These there are like, and these approaches can be like subjects by itself. And one of those approaches is called neural networks. And neural networks is a structure where you train a model to mimic, just like it mimics the connection of neurons in our brain. It was actually taken from that. And based on that, it was created the neural networks. And deep learning is actually a further application of neural networks. So technically, it is a supervised learning process. Or
Okay.
maybe there are some applications of deep learning which can be hybrid. So there is like semi-supervised learning processes as well. But yeah, so essentially it's the same principle.
And also, like, I also wanted to know properly, like, I have read about them, but never quite understood what are exactly convoluted neural networks.
And honestly, I cannot help you there because I have never like really like I've studied neural networks but never did any work in there. So my understanding of neural networks is very basic. But if you really want to know, I would actually suggest like do the course in Udacity because that actually like is helpful. It would be helpful if you want to know this thing. What happens in industry is that you start working in some particular group of algorithms and then you stay there. You do not really like explore other algorithms, other avenues unless you actually need to, because we also have to optimize our time and our effort. Since we do not really apply neural networks in our work, we don't really use it. We use other algorithms like naive based classifications and like some unsupervised classifications like spectral learning, etc., some like PCA and stuff, and so that's why we just stay within that realm.
Okay, thank you.
Yeah. Okay. Any other questions?
So could you use machine learning for
Hello. I
sort of
Yeah.
designing proofs using a computer?
I'm sorry. I didn't really
Designing
understand.
proofs as yeah. So could you use machine learning for designing proofs using a computer?
Mining? I'm
So
sorry.
for example, you have a certain mathematical problem and you need to prove it. So could you use machine learning to design proofs using a computer? I'll put it up in the chat actually.
It That's an interesting idea, but I don't think you can use like simple algorithms like naive Bayes or something to design proofs, but you will need some kind of probabilistic method. For example, I know that Monte Carlo simulation is actually used to design proofs of different kinds of mathematical problems. But I also like neural networks like would be a good application because in proofs you actually it's not just a solution that you're looking for, but you're looking for a flow chart. You're looking for a particular like flow of information of how like a particular proof will be reached, and that kind of a model would be suitable for neural networks. But I'm afraid I cannot give you further information on it because even if it sounds a really interesting idea, this is not something like I've ever worked on. But it's interesting. Maybe there is some like literature on it that you can find online.
Thank you, thank you.
There is a question by Avinav Singh in
Mm-hmm.
the chat box.
Okay, Avinav Singh is asking, is there any limit put by algorithms or number of classes, or we can have as many like fruits, then different type of fruit, then ripe, unripe, and so more the number of classes, more the uh, computational power we needed. So that's a good question. So basically, what is the ultimate number of classification? The ultimate number of classification is exactly the number of parts that you have in a database, right? Because if you go until the uniqueness, if you search for the uniqueness, what will happen is that you will find that there is something that defines one single image as a single image. So the total number of classes is actually the total number of points in the database, but that doesn't really help you, right? Because the purpose of machine learning is to simplify things. So you end up in a situation where you actually like overtrain the model. This is actually what we call is like an overtrained model, like an undertrained model. So the most basic assumption where the most inefficient classifier would be where it doesn't give any classification. It says that okay, this entire group of oranges is one class, And the most stringent classification would be, it will say that every single element contains a particular class, and both of these are like, they do not help you. What really helps you is a middle point, and that actually, like, it's actually achieved most of the times by trial and error. Sometimes you have to trial a lot of times and see, like, given the computational power you have, what is the most expected value that you can run into. But yeah, I do not think there is a limit put by algorithms itself. It's the computational power that that defines whether you have a limit to how many classes you can define. I think you can define as many classes as you want.
Actually, regarding computational power, may I ask one question? Like, are we thinking about using machine learning and deep learning networks for, I mean, rather via quantum computers as well?
I don't know. I'm sorry, because quantum computation is not something that I deal with. But perhaps there are like the like honestly, like, maybe you can help me out here and knowing, like, what is the difference of computer, like quantum computer, in terms of efficiency. I know that, like, a probably a mathematical problem that can be solved in a single computer, like a standard computer, in some time, a quantum computer can actually solve it in a fraction of a time. But that helps machine learning, of course. But what is, like, how is it different?
Like,
I would be able
like
to.
it's different as in that quantum computer uses qubits, as in the superposition between 0 and 1, and it can like keep shifting in that superposition, and here we have definite zeros and ones in the circuit.
Yes, but that also relates to how you store data and how you create the database, and maybe that becomes faster. But in like, the only thing I think it helps in machine learning is it'll be faster to classify something. But I don't know how actually speed relates to, like, actual writing, actual algorithmics, the actual statistical concepts, because it doesn't really work, like, it doesn't really affect, I think. I think the standard machine learning algorithms would work in a quantum computer just fine, but that is just my assumption.
Okay.
There is another question in chat box.
Okay, so Avinav Singh is, yeah, overtrained model fits the test data highly accurate but does not fully
In a
classify data.
hypothetical scenario, if we were to have, in a hypothetical scenario, the question is the number of days.
Cheshmar, I would say just wait for a moment, because there is a question from Avinav Singh in the chat box, which says that overtrained model fits the test data highly accurate, but does not fully classify training set so well. So, what is an optimal level of fitting the data? Does it depend on our use or the kind of data? Well, it depends on both. It depends on what kind of information, what kind of intelligence do you want from the what kind of intelligence you want from the data, and also it depends on what kind of information is already provided in the data. So it's always like the combination of information that you need. So, like, in the industry, what we level is that it's the query that takes precedence, like what kind of information that you want from the data, that takes precedence. Sometimes that can dictate that what you need is a basic classification, because I work mostly with, in like, microelectronic components, data related to microelectronic components, where you have to look at the physical characteristics of some parts and say whether it's a capacitor or an inductor or a resistor or something like that. And sometimes you can actually go deep down into the specifications, but sometimes you can just look at the operating temperature and say that, okay, a capacitor cannot work in that particular operating temperature, so yeah, this is not a capacitor. This An inductor will not work in that, like, high degree of tolerance, so that's not an inductor. So it's ultimately it's the query that dictates, like, what should be the optimal level of fitting. Yes, Orchishman, tell me, like, sorry for interrupting. So, Orchishman is saying in a hypothetical model where we have as many classes as data, uh, as many classes as data points, would we not end up with being too specific? Yes, exactly. That's the problem. So, in a hypothetical situation where you have every single class as a data point, then it's not really different from the database itself. So, you all that effort actually goes to waste here. Then you cannot really classify.
Hello.
Yes.
Yeah. So I was saying that if is there anyone who has some any question, or we are about to sign off? I was just asking to other people, not to you here.
Yeah, I understand.
Yeah.
Yeah.
Yeah. Oja sir has some question.
Yes, Oja sir asks, do you consider nature of distribution in our data such as normal? Um, Not always. Not always. Sometimes when we look at graphical data, we can, but it's not always a valid thing because we start with the assumption that all the data that mostly appears in reality has some sort of a normal distribution. So, considering that, we proceed with the data. So no, whenever we are trying to classify a data set, whether the probability distribution of the data or some variables doesn't really play a huge impact. Sometimes it does whenever for some specific like probabilistic learning methods, it's important, but that's very rare. That's very rarely used in like our in the industry, at least in like in my experience. Thank you, sir. Thank you for joining.